So the next thing we want to do is we want to take a look at a very specific type of separable differential equation. And that differential equation has the form dy dt. We're going to use t here to represent time, is equal to some constant k times y. So essentially what we're saying is the rate of change of the variable y with respect to time is proportional to y itself. We also have some conditions that y is equal to y0, or initial amount, when t is equal to 0. So the first thing we're going to do is we're going to solve this differential equation. So we have dy over y is equal to k dt. We're going to integrate both sides of that, and we get the natural log of the absolute value of y, because we can only take logs of positive numbers, is equal to k times t plus some constant c. And if you recall, natural log is log base e, so exponential base e is the inverse of that. So what we're going to do is we're basically going to take e to the power of both sides and get the absolute value of y is equal to e to the kt plus c. Using properties of exponents, we can write this as e to the c times e to the kt. And what we're going to do now is we're going to solve for y, so get rid of the absolute value, and we have plus or minus e to the c times e to the kt. And then we look at our initial conditions. So our initial conditions are the following. y0 is equal to plus or minus e to the c times e to the 0, but e to the 0 happens to be 1. So the initial amount, we're calling it, happens to be plus or minus e to the c. So in our equation, we're going to replace plus or minus e to the c with y0. So we go back to basically this point right here, and we say y is equal to y0 times e to the kt. And you probably recognize that as an exponential function with an initial value of y0, and we're using a base of e, and e, as you know, is approximately 2.71. So what do we have? We have the following. If k is greater than 0, we have growth. And if k is less than 0, we have decay. Now that decay thing might not be as obvious, but if you take e to the, let's say, negative 2t, that would be the same as writing it as 1 over e squared, the whole thing raised to the t power, in which case your base is going to be between 0 and 1. And you probably remember talking about exponential growth and decay. If your base is greater than 1, you have growth, and if it's less, between 0 and 1, you have decay. So this idea of exponential change is summarized in this table right here from our textbook. If y changes at a rate proportional to the amount present, basically what they're saying is if dy dt is equal to some constant times y, and y equals y0 when t is equal to 0, then we have this equation right here, which we just derived. It's growth if k is greater than 0, and it's decay if k is less than 0. So what I'd like to do next is a few examples of that. So let's start with this example. We have dy dt is equal to k times y, and we know that y is 50 when t is equal to 0. So remember, this would be our t value, and this would be our y0 value. All right, so we can go through and we can separate this and solve, or if we just recognize this situation that the rate of change of y with respect to time is proportional to y, then we can simply write y is equal to y0 times e to the kt. And we're going to plug in what we know, and we know that y is equal to 50 times e to the kt. So what we need to do is we need to be able to solve for k. Another piece of information that I did not initially provide in this problem is that y of 5 is equal to 100. Okay, so basically we know that when t is equal to 5, y is equal to 100. So it appears we have a case of growth here, and we're going to verify that by finding the value of k. So 100 is equal to 50 times e to the 5k by plugging in 5 for t, and then we're going to solve that. So we divide both sides by 50 and isolate the e to the 5k, so we have 2 is equal to e to the 5k, and if you remember solving exponential equations, you can either write them with the same base or you can use logs. In this case, writing them with the same base would be extremely difficult, so we're going to use the natural log of both sides, and the natural log of e to the 5k is simply 5k. So 5k is equal to the natural log of 2, and k is equal to natural log of 2 over 5. So you can grab your calculator at this point and verify this, but if you find k is 0.139 to 4 decimal places. And since k is greater than 0, we have a case of growth. So our function is y is equal to 50 e to the 0.139t, and that is an example of exponential growth. And if you'd like to further verify that, take into consideration rounding, you can verify that y of 0 is 50, that's easy, and y of 5 should be approximately equal to 100, minus the rounding errors. So the next thing I'd like to do is I'd like to talk about the idea of a half-life, because half-lives are associated with exponential decay. So if we were to look at a half-life situation, what we would say is something like this. 1/2 of the initial amount is equal to y0, the initial amount, times e to the, we're going to write it as negative kt, because we know it's exponential decay, and the exponent, or the k value, is going to be negative. So what we want to do is we want to actually solve this equation for the time, which would tell us the half-life. How long does it take for the initial amount, y0, to decay to half the initial amount? So we would divide both sides by y0, and we would have 1/2 y0 divided by y0 is equal to e to the negative kt, or basically 1/2 is equal to e to the negative kt. So then what are we going to do? We're going to take the natural log of both sides. So the natural log of 1/2 is equal to the natural log of e to the negative kt, or negative kt is equal to the natural log of 1/2. And if you remember your properties of logs, you can separate that natural log of 1/2 to the natural log of 1 minus the natural log of 2 is equal to negative kt, and the natural log of 1 happens to be 0. So what do we have? We have the natural log of 2 is equal to k times t, or the half-life, t, is equal to the natural log of 2 divided by k. So essentially, you can say for any problem, the half-life is equal to the natural log of 2 divided by k when k is greater than 0 And the reason that k is greater than 0 is because up here in the original, we dealt with the fact that our exponent needs to be negative by making k have a negative sign in front of it. So we're going to end this video with a half-life problem, and this form of the equation, y is equal to y0 times e to the kt, or negative kt, where k is greater than 0, isn't very conducive to thinking about half-lives. What we'd like to do is write it in a form y is equal to y0 times b, and we're going to say to the ht, and we would like b to be equal to 1/2. So what we need to do is we need to figure out what h is. So here's a typical half-life problem that you may have done in Algebra 2 or pre-calculus. And in this situation, what do we know? Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So at this point, we're really not doing a calculus problem. We're basically doing an Algebra 2 or a pre-calculus problem. So what are we going to do? We're going to use a convenient base, and we're going to write this as y is equal to y0 times b to the ht. And here's why you'd want to use a convenient base, because basically we're going to use 1/2 as our base, and we want to know that every 5,700 years the initial amount, we'll call it y0, decays to half what we started with, or half that amount. So basically what we need is we need h to be equal to 1 over the half-life of 5,700. So we have the following. We have 1 over 5,700 times t. And why would that be? Because after one half-life, 5,700 years, our exponent would be 5,700, so we would multiply by 1/2. And in this case, we're being told that the sample in which 10% of the radioactive nuclei originally present have decayed. So basically what we're saying is we have 90% of the original amount. So that's our setup. At this point, we're simply solving for t. So if we divide both sides by y0, they are going to cancel out, and we have 0.90 is equal to 1/2 to the t over 5,700. And now we're going to have to take logs of both sides. All right, you can use any log base you want. I'm going to use natural log, so natural log of 0.90 is equal to natural log of 1/2 to the t over 5,700. But properties of logs, that t over 5,700 can come down here, so we have natural log of 0.90 is equal to t over 5,700, natural log of 1/2. Divide both sides by the natural log of 1/2, natural log of 1/2 on both sides, natural log of 1/2. All right, do not make the mistake of taking natural log of 0.90 minus natural log of 1/2. That is not the log property. The log property would be natural log of 0.9 over 1/2 can be written as natural log of 0.9 minus natural log of 1/2. Here we have two separate logs, so we can't use that property. Natural log of 1/2 cancel out on both sides. Multiply both sides by 5,700, and we get 5,700 times the natural log of 0.90 over the natural log of 1/2 is equal to t. And if you verify that with your calculator, you will get t is approximately 866. And if we assume that we're working in years here, or did the problem state that? It's in years. So we have approximately 866 years. In other words, carbon-14 will decay to 90% of its original amount in approximately 866 years.